In this video, we solve exercise 118 from section 5.5 of the Larson Calculus text, 10th edition. We're given this function. It's a quotient involving exponential functions of a base other than e. Well, actually, the base could be e. We're asked to show that this function f has an inverse, and then we're asked to find f inverse. Here we're assuming a is a positive number and a is not equal to 1. There are a couple of things that we might be interested in learning. In order to analyze this function, we might be interested in its behavior as x goes to positive and negative infinity. So let's look at the limit as x goes to infinity of f of x. First of all, I notice that if a is greater than 1, this is an infinity divided by infinity, indeterminate form. And it looks like, oh, I got it. There was a little bug. I think I got rid of it. So as if a is greater than 1 and I raise it to a large power, that's going to be a really large number minus 1. And this is going to be a really large number plus 1. So it's an infinity over infinity indeterminate form, but I notice that this is basically the same number as this. The only thing is that I've subtracted 1 from the numerator and I've added 1 to the denominator. So I'm really expecting this to have a finite limit. One way that we can find that finite limit is we can divide the numerator and denominator by the sort of dominant function in the denominator. When we had polynomials, we had a tendency to divide by the highest power of x in the denominator to make the to get rid of the indeterminate form, that infinity over infinity problem. In this case, rather than dividing by the highest power of x, we can divide by that a to the x in the numerator and denominator to get rid of the infinity over infinity problem. So we will take all of this and divide by a to the x. That's legal as long as we do the same thing in the denominator. So really all we're doing is sort of multiplying by a well-chosen one and then choosing to divide each of those by the same thing. It doesn't change the value of it at all. A to the x divided by a to the x is 1. And then if I have negative 1 here, I've got negative 1 divided by a to the x here. This is where we're assuming that a is greater than 1. Now, assuming that a is greater than 1, this is 1 divided by a very large number as x goes to infinity. So this is going to go to 0, and this is going to go to 0. And so we get a limiting value of 1 in that case. So if the limit as x goes to infinity of f of x equals 1, that means y equals 1 is a horizontal asymptote of the function. Now, we might also be interested in the behavior at negative infinity of f of x. Say, okay, well, what happens to this function as x goes to negative infinity? Now, you might be tempted to think that this is an indeterminate form as well, but it's actually not. Because if a is greater than 1, the graph of a to the x just looks like this. It's an increasing function. As x goes to negative infinity, this is a to a large negative power. That's going to be, like, let's say we have a to negative 1,000. That's the same as 1 divided by a to the 1,000. And if a is greater than 1, this is a large number. So 1 divided by a large number is a very small number. Or alternatively, we can just look at the graph of y equals a to the x and say, what happens as x goes to negative infinity? The y values get closer and closer to 0, of course. So the limit as x goes to negative infinity of this, provided that a is greater than 1, is this 0 minus 1 divided by 0 plus 1. And so we get negative 1 divided by positive 1, which is negative 1 there. And if the limit as x goes to negative infinity of f of x is negative 1, that means that y equals negative 1 is a horizontal asymptote of the function or the graph of the function. So with that in mind, we know that the function f of x, where a is greater than 1, looks kind of like this. This is y equals 1. This is y equals negative 1. And as x goes to a positive infinity, y is approaching 1. And as x goes to negative infinity, y is approaching -1. And at x equals 0, I have a to the 0, which is 1. 1 minus 1 is 0. Divided by a to the 0, which is 1. 1 plus 1 is 2. So I get 0 divided by 2, which is 0. And it actually looks kind of like this. And different values of a change the slope a little bit. But that's roughly what it looks like. And if our a value happens to be between 0 and 1 rather than being greater than 1, instead of a to the x looking like this is where a is positive, and that, or not positive, strictly greater than 1. If a is a fraction, so some number between 0 and 1, rather than increasing as you go from left to right, it decreases as you go from left to right. So in that case, if my f of x is a to the x minus 1 divided by a to the x plus 1, if I look at the limit as x goes to infinity of f of x in this case, remember what that a to the x looks like if a is between 0 and 1? It's a decreasing function. I think of 1/2. If I keep multiplying by 1/2, that function value is going to be like half as large as it was a second ago, and then half as large as it was the last time, and half as large as it was the last time. You just keep multiplying by 1/2, so the values of the function as you go from left to right just keep getting smaller and smaller. That's going to be that will be true for any fraction between 0 and 1, any proper fraction. So if I'm looking at this as x goes to infinity now, and say, well, what happens to the y values on my graph? As x goes to infinity, the y values are approaching 0. So this is going to 0 and this is going to 0. Again, because our a is actually a fraction, a proper fraction. If I take 1/2 and I raise it to a really large power, 1/2 to the 1,000, well, that's like 1 to the 1,000th over 2 to the 1,000. So I end up with 1 divided by a very large number, which is a very small number. So this goes to 0 as this exponent gets larger and larger, if this is a proper fraction. So we get 0 minus 1 over 0 plus 1, which is -1. So y equals -1 is a horizontal asymptote of the graph of the function or the function itself. And then as we go to negative infinity, if our a is that proper fraction between 0 and 1, the y values go to positive infinity on that graph. And of course, this is just a to the x. Our function f of x is actually a to the x minus 1 divided by a to the x plus 1. So as we go to negative infinity, this is approaching positive infinity, because as we go farther and farther to the left here, the y values increase. So this is going to positive infinity, and this is going to positive infinity. So this is an infinity over infinity indeterminate form. We can get rid of that problem if we divide by that dominant term, which is that a to the x in the numerator and denominator. We do the same thing in the numerator that we do in the denominator. It's just multiplying or dividing by a well-chosen 1. It doesn't change anything. A to the x divided by a to the x is 1. Then we have -1 divided by a to the x here. And then I have a 1 plus 1 over a to the x here. Now you want to be careful with this. As x goes to negative infinity, this a to the x actually goes to positive infinity. So we're going to have, and it's because we're taking a fraction and raising it to a large negative power. So for example, if I had that 1/2 again raised to the -1,000, because of the fact that a divided by b to the negative n is b divided by a to the positive n, because that's true, this a to the x is getting very, very large. Or alternatively, you can think about it in terms of the graph again. As x goes to negative infinity, a to the x gets very large if a is between 0 and 1. So you say, okay, this is -1 divided by a very large number. So that's going to be a very small number. And the same is true for this. So we end up with 1 divided by 1, which is 1. So y equals 1 is a horizontal asymptote of the function. So in this case, when a is between 0 and 1, we still have those horizontal asymptotes. We want to be careful though. This says as x goes to positive infinity, y approaches -1. So as x goes to the far right, the function approaches this curve. And then this says as x goes to negative infinity, y approaches +1. So as we go to negative infinity, it looks like that. And then if we evaluate this at x equals 0, we have a to the 0 minus 1, which is 1 minus 1 or 0 in the numerator, divided by 2 in the denominator. So we end up with a 0 again. And sort of roughly, it's going to look like that. So the function seems to be decreasing. We'll prove that in just a moment. But that's sort of the general behavior of this function, or at least the end behavior as x goes to positive and negative infinity. If a is between 0 and 1, it kind of looks like that. And if a is if a is greater than 1, it looks like that, where it's increasing. And if a is between 0 and 1, it looks like this, where it's decreasing. And you might say, how do you know? I thought we only analyzed the end behavior. Well, we'll figure that out in just a moment. So this is roughly what the graph looks like. If we want to, we can graph this on Desmos.com and then look at the graphs for various values of a. I'd like to do that. So this is what the graph looks like for a equals 3.74. Now, I have a slider here for a between 0 and 10. If I let a just go between 0 and 1, watch what happens. When a equals 0, we just have the function 0 there. But if a is between 0 and 1, I like watching the graph change. We see that the function is decreasing. And it sort of flattens out in the middle, but the function is decreasing as you go from left to right for all of those different values of a. Now, in general, the a value is fixed. So you might have, well, a equals 1/2 or something like that, or a equals 5/4. So let's say a equals 1/2. That's what the graph looks like if a equals 1/2. If a equals 3/4, it looks like that. If a equals 4/5, it looks like that. If a equals 1/10, it looks like that. Or 1/100th, it looks like that. We see that the function is decreasing if a is between 0 and 1. Now, if a is greater than 1, let's say a is between 1 and 10, the function looks like this. It's increasing. And as that base approaches 10, we see that the slope of the tangent line in the middle seems to increase. Actually, it seems to approach sort of a maximum of 1, I think. Kind of cool watching that change. But in general, for a particular value of a, the graph looks like that. So for a equals 5.83, we have a function f of x equals 5.83 to the x minus 1 divided by 5.83 to the x plus 1. And the graph looks like this. It has the vertical and horizontal asymptotes at y equals 1 and y equals -1. So the question is, does this function have an inverse? And we say, yes, it does. For every value of a, I'll just use this representative value of a for a between 1 and 10. We can see that the function passes the horizontal line test. Remember, the horizontal line test says that every horizontal line passes through the graph at most once. So maybe the horizontal line doesn't pass through the graph at all because that particular y value isn't in the range of the function. But if that particular y value is in the range of the function that corresponds to that particular horizontal line, then that horizontal line crosses the graph at most once, crosses the graph once. So we can see that. I'm just letting y go from -3 to 3, and then letting that horizontal line pass through the graph. So initially it doesn't pass through the function at all, and then it crosses once. So it doesn't pass through the function, and then it passes through the function at that purple dot. You see it only crosses once. And that's kind of what the graph looks like for a representative value of a between 0 and, or between 1 and 10, where the function is increasing. But we could let a change, and we could let that horizontal line pass through the graph as well. But we see when the function is increasing the whole time, that horizontal line only crosses the graph once. Now, if our a is between 0 and 1 instead, we see when the function's decreasing, that horizontal line only crosses the graph once, at most once. And it only crosses when the y value for that y equals c is in the range of the function, which is from -1 to 1. All right, so I think we get the idea. It passes the horizontal line test. Now you might say to yourself, what if I didn't have Desmos-Smith-Townsend? I don't know what the graph looks like. I'm just guessing. I know what the end behavior is. I know how the function behaves as x goes to positive and negative infinity. We know it approaches plus or minus 1, depending on whether a is a proper fraction or if a is greater than 1. Say, but I don't really know what happens in between. I mean, what if there are lots of hills and valleys in between? Then the function wouldn't be 1 to 1. And if the function had minima and maxima between those sort of that end behavior, then the function would not have an inverse. So how can we infer that the graph is 1 to 1 in general? Well, remember, we can take the derivative. And if the derivative is positive for the entire domain, which is all real numbers, or if the derivative is negative on the function's entire domain, which is all real numbers, then we know that the function is 1 to 1. And I think we can see just from graphing this that when a is a proper fraction, the function is decreasing. And since it's strictly decreasing, the function is 1 to 1. It's monotonic. Every x value has only one y value, and every y value has only one x value. And then if a is greater than 1, the function is strictly increasing. So we call that monotonic. And if the function is strictly monotonic, then it has an inverse. You say, how can I prove that? Well, just take the derivative and analyze the sign of the derivative. So let's do that. We'll do that on paper. So we want to compute f prime of x, and f of x was that a to the x minus 1 divided by a to the x plus 1. To compute that derivative, we'll use the quotient rule. We'll call this the low function and this the high function. According to the quotient rule, we get low d high. So it's the bottom function times the derivative of the top function. Now the derivative of a to the x is natural log of the base times the exact same exponential, and then we subtract the derivative of 1, which is just 0. This is low d high, so that the bottom function times the derivative of the top function minus high, and then d low is natural log of the base times the exact same exponential, and then we divide by low, so that's a to the x plus 1 quantity squared. Now, if we want to, we can distribute this natural log of a times a to the x to this expression, and distribute the natural log of a times a to the x and the -1 to this expression. If we do that, we get natural log of a, and a to the x times a to the x, we just add the exponents because the bases are the same. That's a to the 2x. We're adding that to 1 times natural log of a times a to the x. Now here, if I distribute the negative and the natural log of a times a to the x to this a to the x, I'll have negative natural log of a, and then a to the x times a to the x is a to the 2x because we're adding the exponents. And then -1 times -1 is +1, and then we're going to add a natural log of a times a to the x. Well, I've already got one of those, so I'll just put a 2 in front of that. So I'll have two of them after we distribute that term and then collect like terms. That's our numerator. And we see that we've got two terms with opposite signs in common, so those reduce. And in our denominator, we've got a to the x plus 1, quantity squared. And this is f prime. Now we know that no matter what a is, if a is positive, the function values on the graph of y equals a to the x are positive the whole time. Y equals a to the x looks like this if a is greater than 1. Y equals a to the x looks like this if a is between 0 and 1. But if you look at the y values, the corresponding y values, the range starts at 0 and goes to infinity for both of these. So all of these y values between 0 and infinity are associated with x values on the graph of the function. Y is never equal to 0, but we get all of the y values between 0 and infinity here. If a is greater than 1, the function is increasing. If a is between 0 and 1, the function is decreasing. But we can see that the function lies entirely above the x-axis, which means that all the y values are positive. So a to the x is positive. If I take this positive number and I add 1, this expression is greater than or equal to 1, and we square it. So that's still a number that's greater than or equal to 1. So this is positive. But natural log of a could be positive or it might be negative. We know natural log of x looks like this. When x equals 1, natural log of 1 is 0, so that's the y value there. Natural log of x is going to be negative anytime that x value is between 0 and 1. So if I substitute an a instead of an x, we're going to get a negative value for natural log of a when we're between 0 and 1, and a positive value for natural log of a when a is greater than 1. So this is a positive divided by a positive squared, which is positive. But and then we've got the 2 times natural log of a. So the sign of f prime is determined by the natural log of a. So this f prime, we see f prime is negative for all real numbers x. So that's all x in the domain of the function. Having problems with my pen. When a is a proper fraction. And that's because in that case, natural log of a is a negative number. Again, we're talking about those y values on the graph of natural log of x, where x is between 0 and 1. Now, if f prime is negative the whole time, that means that f is monotonic. It's just sort of a definition of monotonic. And if f is strictly monotonic, then f has an inverse. And again, you say, well, what does the graph look like? Well, I don't know exactly what it looks like, but it looks roughly like that. We know that the end behavior is that it approaches y equals 1 as x goes to negative infinity. The function approaches y equals negative 1 as x goes to positive infinity, and then it decreases in between. So roughly it looks like that, and we saw what the graph actually looked like for different values of a between 0 and 1. Now, if a is greater than 1, we know that natural log of a is positive because we can look at the y values on this graph and we see that those y values are above the x-axis, so this is positive. And when x is greater than 1, or in this case, when a is greater than 1. So we've got a positive number times a positive number divided by a positive number, which is a positive number. So f prime is positive for all x in the domain when a is greater than 1. And again, that's because natural log of a is going to be positive because a is greater than 1. So that means f is strictly monotonic. And if f is strictly monotonic, that means that f has an inverse. Or in other words, f is 1 to 1. Every x value has only one y value. And every y value has only one x value. So if we switch the roles of x and y, the graph of the resulting relation is actually a function. Okay, so we have determined that f has an inverse. And the question said, show that f has an inverse. Now we've shown it. And then we're asked to find f inverse. To find f inverse, it's relatively simple. You just replace f of x with y, and then you solve for x as a function of y. So let's do that. So I have f of x equals a to the x minus 1 divided by a to the x plus 1. We're replacing f of x with y, and now we solve for x. So we're solving for x as a function of y, essentially. Say, okay, how can I get x by itself? Problem is, right now I've got an a to the x in the numerator and an a to the x in the denominator. In order to solve for x, I'm going to need to get all the x's on one side, but I need to get rid of this minus 1 and that plus 1 somehow so that I can simplify everything. To do that, I will multiply both sides by this quantity in the denominator. And then distribute on the left-hand side. So we'll have y times a to the x plus y times 1, which is just y, equals, and then these reduce, a to the x minus 1. And we're trying to isolate that x. So I need to get rid of this minus 1 on the right. I can do that if I add 1 to both sides. And I want to move this x term to the left. No, I want to move this x term from the left to the right. So I'll subtract y times a to the x from both sides. If I subtract those, I have a y plus 1 on the left-hand side. And then on the right-hand side, I have an a to the x minus y times a to the x. Now, since both of these terms have an a to the x in common, we can factor out that a to the x. And so we have y, or y plus 1, equals a to the x times 1 minus y. And then we'll divide both sides by 1 minus y to get that exponential expression by itself. And you say, okay, well, how do I get x by itself now? Well, if a to the x is equal to 1 plus y divided by 1 minus y, in order to get rid of that that a to the x, I compute the log base a of both sides. So I have log base a of a to the x on the left and log base a of y plus 1 divided by 1 minus y on the right. Now, since log base a of x and a to the x undo each other, we just end up with an x on the left. So x as a function of y is log base a of 1 plus y divided by 1 minus y. Now, before we move on, one thing I want you to notice is that this equation is actually equivalent to the original equation. So the set of points x, y that satisfy this equation also satisfy the equation y equals a to the x minus 1 divided by a to the x plus 1. These are just two different ways of writing the same equation. It's like taking y equals e to the x and saying that's equivalent to, well, if I take the logarithm of both sides, natural log of y equals x. So here I have x as a function, or y as a function of x, and here I have x as a function of y. But either way, if I graph those, it's just the graph of y equals e to the x. So these are just two different ways of saying the exact same thing. Now, that's almost my inverse function. If I switch the roles of x and y, and then call the new y f inverse of x, then we've defined an inverse function. Then the inverse of y equals e to the x is y equals natural log of x, which comes from taking this x as a function of y and switching the roles of x and y. So if I switch the x and y here, I'd have y equals natural log of x, which is the inverse of e to the x. And then if I graph it, it looks kind of like that. So notice this is x equals natural log of y, which is equivalent to this. This is y equals natural log of x, which is the inverse. And we have that symmetry across the line y equals x. So here, this is not the inverse. This is just another way of writing the same equation. If I switch the roles of x and y now, so instead of having x as a function of y, I have y as a function of x equals log base a of 1 plus x divided by 1 minus x. So I'm replacing all my y's with x's, and I'm replacing all my x's and y with y's. This y is not the same as the original y. This y is actually f inverse. So we're going to call this f inverse of x equals log base a of 1 plus x divided by 1 minus x. Now, that is our inverse function. You might say, well, what does it look like? Well, remember that f of x, let's just say that a is greater than 1. If a is greater than 1, the function is increasing, and it looks roughly like this. As x goes to negative infinity, the y values approach y equals -1. As x goes to positive infinity, the y values approach 1. And this is f of x equals a to the x minus 1 divided by a to the x plus 1 for a greater than 1. That's so the basic shape, and of course the particular value of a determines the exact shape, determines the slope at each location. Because remember what that slope function was. The derivative is actually dependent on a. It's 2 times the natural log of a, which is some particular number, times the original exponential, divided by that exponential plus 1 squared. The slope depends on what a is. But this is the basic shape of that. That's f of x. You might say, okay, well then what does f inverse look like? Well, f inverse is going to look very similar, but we switched the roles of x and y. So the original graph had horizontal asymptotes at y equals 1 and y equals -1. The new graph is going to have vertical asymptotes at x equals 1 and x equals -1, because we switched the roles of x and y. Here, as x goes to positive infinity, f of x, which is y, approaches 1. And here, as x goes to negative infinity, f of x, which is y, approaches -1. Now, if we switch the roles of x and y, as x approaches -1, and we're going to approach from the right, then f inverse of x has to approach negative infinity. And as x approaches +1, because we're switching the roles of x and y, this time we're going to approach from the left, then the y values have to approach positive infinity, or f inverse values have to approach positive infinity. So you could use y instead of f of x here, and you could use y instead of f inverse here, but I'm using f of x and f inverse of x because those are 2 different functions. So if we put those 2 pieces together, as x approaches -1 from the right, the y values go to negative infinity. And as x goes to +1 from the left, the y values go to positive infinity. And I want to try to draw something that has like roughly the same slope. So I think it's going to look roughly like that. This is f inverse of x equals log base a of 1 plus x divided by 1 minus x. So that's what the graph looks like if we switch the roles of x and y. I think we can see that switching the roles of x and y here gives us a graph that looks roughly like this. So you can almost imagine just taking this graph and then turning it this way, but then you have to reflect it. You have to do a reflection in order to make it look like this. Does that make sense? I hope it makes sense. All right. let's look at this graph on desmos.com and make sure that our graph is consistent with our expectations. Now both of these graphs are for a greater than 1. If a is less than 1, instead of increasing as you go from left to right, if a is between 0 and 1, it's going to decrease. And if this decreases here, then the limits switch. So we would end up, instead of going like this as you go from left to right, it would go like this as you go from left to right. If the original function is decreasing, f inverse is also decreasing. If the original function is increasing, f inverse is also increasing. And we know that because we know that the rates of change of f inverse and the rates of change of the original function f are reciprocals of each other at corresponding points. So the derivative of f inverse at x is equal to 1 divided by the derivative of f of the original function f at the corresponding y value. And so we know that that's true from our previous studies. But let's look at these graphs on Desmos, and we'll look at them for a representative value of a that's greater than 1, and we'll look at them for a representative value of a that is between 0 and 1. Okay. So that was our horizontal line test. We said we can also show that f is 1 to 1 by computing the derivative. We used the quotient rule, we simplified. And we said f prime actually looks like this. Now this is a graph of f of x and its derivative when a is a proper fraction. I don't remember what a is here. Let's see. This is when a equals 0.2245. Let's have a equals 0.5. Whoops. And 1/2. I think I actually like that 0.2 better. It gives you a better slope. So a is 1/5 essentially. So it decreases as you go from left to right. If you look at the derivative of that function, if you graph it, we see that the derivative is negative the whole time. The y values on that derivative graph are negative. Again, it's because we've got a to the x, which is always positive, a to the x plus 1 squared in the denominator, which is always positive, and 2 times natural log of a, which is negative, because natural log of 0.2 is negative. Natural log of any number between 0 and 1 is negative. So we've got a negative times a positive divided by a positive, which makes the resulting derivative negative for all real numbers. And that's consistent with what we see for the original graph. The original graph is decreasing because, and that's consistent with the fact that the derivative is negative. So that's what the graph looks like. That's what the graph of f looks like and the graph of f prime look like for a between 0 and 1. So when a is a proper fraction. We talked about solving for f inverse. We did all of these calculations on paper. And this is one thing I wanted to show you. I told you that if we just solve for x as a function of y, we get the exact same curve. So if I ask Desmos to graph x equals log base a of y plus 1 divided by 1 minus y, notice it's the same thing. I haven't changed anything at all. It isn't until I replace x with y and y with x, and then call the y f inverse, that I actually get the inverse function. So this is x is a function of y. And then this is what happens when I switch the roles of x and y and let y be a function of x, where this y is no longer the original y. Now it's called f inverse. And we see that graph. And if we want to, we can say, since the original graph had horizontal asymptotes, y equals 1 and y equals -1, the new graph has vertical asymptotes, x equals 1 and x equals -1. And it's easier to see if we get rid of the graph of the original function. So let's get rid of that real quick. And so we said the original function f of x was decreasing on its domain. So when you compute f inverse looks like this, and it's also decreasing on its domain. Now, if we want a to be greater than 1, let's say a equals 5. We'll let a be between 0 and 10 now, and let a be 5. Now, instead of decreasing, the function increases, or the inverse function increases. And that's what the original function looks like. So there's our original function. It's increasing on its domain, therefore it's 1 to 1. And since it's 1 to 1, it has an inverse. We computed the derivative, we simplified because we understand what the logarithm looks like. We were able to infer the sign of f prime based on the sign of log of a. We switched the roles of x and y. After solving for x as a function of y, this is the inverse function, just for a representative value of a. Now, if you want to, you can let a change. I just like seeing the curve change. I think it's pretty. So if a is between 0 and 1, the function will be decreasing. If a is between 1 and infinity, the function will be increasing. If you just let that run, you can see the slope change a little bit for different values of a. I just think it's pretty. I like sliders. It's for some pretty graphs. All right, so that's problem or exercise 118 from section 5.5, which featured a function that involved a to the x. We were able to graph it using our understanding of function or limits of functions at plus or minus infinity, and the derivative of a function. Then we were able to say, okay, since the derivative is either always positive or always negative, the function has an inverse, and then we were able to solve for that inverse.